Alright. How's it going? How's it going today? I'm doing well. So, we should do some research. As much as I want to talk about politics all day, we need to do some research. Feels bad, man. Feels bad when you want to do something, but you gotta do something else. But hey, that's part of life. Alright, let's get started on that. So, let's go through the CPU change. So, let's take a look. Linux 7.0 now defaults to Intel TSX Auto Mode for performance benefit on newer CPU. Intel Transactional Synchronization Extension has big potential for being a big help to some workloads for greater performance via optimized locking protocol to lock elision. But various security vulnerabilities affecting TSX over the years have given it a bad reputation, even though newer Intel Xeon processor have TSX without those earlier vulnerabilities like TSX async abort. Thus, a patch raised by SUSE set Intel TSX by default to auto mode rather than off, where it's then left up to the user administrator to enable TSX support. TSX auto mode enables TSX on capable hardware where it's believed to be safe against side channel attack, like the likes of Ice Lake, Sapphire Rapids. Okay, we're gonna have to get the dates on that. Okay. Oh, we have a... That's not bad. God damn. Holy shit. Let's see the comments. The comments are always fun. Bring me some joy. Aw. Okay. Can we have a real understanding of what Intel TDX does? TSX. I mean, goddamn. The naming scheme, what the fuck? Okay. That's a microcode. Goddamn. When the first thing on top is like, yep, we disabled it. That feels bad. Okay. Is an extension to the x86 instruction set architecture that adds hardware transaction memory support, speeding up execution of multi-threaded software through lock elision. Okay. Okay, I guess they will explain it here. Okay, TSX, TSX and I. What do they mean by TSX and I? Oh, new instruction. Okay, the other name. Let's just call it TSX. Provides two software interface for designating code region for transaction execution. Hardware lock elision is an instruction prefix based interface designed to be backward compatible with processor without TSX support. Restricted transactional memory is a new instruction set that provides greater flexibility to programmer. Okay. TSX enable optimistic execution of transactional code region. The hardware monitors multiple thread for conflicting memory access while aborting and rolling back transaction that cannot be successfully completed. Okay. Mechanisms are provided by the software to detect and handle failed transaction. Okay, can we have an idea of this? Hardware lock elision adds two new instruction prefix, X acquire and X release. These two prefixes reuse the opcode of existing repne and repi. Okay, what are they? Repeat string operation. What the fuck does that? Repeat a string of instruction a number of times. Okay. On processors that do not support hardware lock elision are ignored in section for which the oh, okay. I think I get it. The prefix, like that prefix doesn't make sense to be used on the instruction that X acquire and X release uses. Okay, so they're not like in the same frame of reference, one could say. They're not used with the same thing. X acquire prefix int can only be used with the following instruction with an explicit lock prefix. Okay. Instruction can be used without the lock prefix as well. X release prevent int can be both with the instruction listed above and with okay, instruction HLE allows optimistic execution of critical section by skipping the write to a lock so that the lock appears to be free to other threads. A failure transaction result in the execution restarting from X acquire prefix instruction, but treating the instruction as X acquire prefix were not present. Whoa, how the fuck does that work? Okay, in other words, lock elision through transactional execution uses memory transaction as a fast path where possible, while slow fallback path is still a normal lock. I'm confused here. I think that I'll have a hard time understanding this, so we'll ask AI and we'll see if there's something on YouTube. Can you explain how Intel TSX works? Thanks. Okay. So that's one thing. Let's just go have a half a second YouTube check.
The objective today is to explain what the Intel manual says about TSX, SHA SHA, okay, and then AVX 512. It's nice that everything's on one page here, but this is spooky. Intel has SHA-1 stuff, and yet there's collisions, so it's broken. We're not supposed to use SHA-1 anymore, but it's there. But I'm getting ahead of myself. Let's talk about transactional synchronization extensions. Simple questions to start. What does TSX stand for? And our first instruction is X abort, so that's abort an RTM transaction execution. So what is an RTM execution? The next instruction is X acquire, so this is a prefix hint to the beginning of an HLE transaction region. And we got X release, X begin, X end, and X test. So that's a nifty little cute small set of X instructions all about transactional synchronization extensions. Let's get to the good stuff. I can hardly wait. These SHA extensions provide a set of instructions.
Bro, you're not going to explain this? What the fuck's the point of listening to you, bro? Goddamn. Intel TSX. Well, I'll be the first one. Intel TSX transaction is a hardware feature built into modern Intel processor that fundamentally change how CPU handles multi-threading and shared memory. To understand how it works, it helps to first understand the problem it was designed to solve, the bottleneck in traditional locking. Problem: pessimistic locking. Imagine a shared bank account. If thread A wants to deposit money and thread B wants to withdraw money at the exact same time, they might overwrite each other's work if they aren't careful. Historically, programmers solve this with locks, mutexes. Before a thread touches shared data, it grabs a lock. If thread B wants to touch the data, it must wait until thread A is completely finished and released the lock. The downside: this is pessimistic. It assumes a conflict will happen if thread A is updating the checking balance and thread B is updating the savings balance. They aren't actually interfering with each other at all. Yet, because the whole account is locked, thread B still has to wait. This slows down multi-core performance. All right, we got this. TSX solution. Optimistic execution. Intel TSX introduced hardware transaction memory. This takes an optimistic approach. It assumes thread won't conflict most times. Instead of waiting for a lock, the thread using TSX will just go ahead and execute their code simultaneously. The CPU treats these instructions as transaction, much like database transaction. Here's how the magic happened under the hood. The speculative run. When a thread enters TSX, the CPU essentially takes a snapshot of the thread state. The thread begins executing its instruction, reading and writing data without actually acquiring the software lock, tracking the reads and writes set. As the thread does its work, the CPU L1 cache secretly tracks everything the thread does. Read set, okay, write set. Crucially, these changes are kept in the CPU's cache and hidden from all other threads. The main memory is not updated yet. The commit. If the thread reaches the end of the transaction and no other thread has tampered with anything in its reads and write set, the transaction is committed. All the change in the L1 cache are instantly made visible to the rest of the system atomically. The abort and rollback. What if thread A and thread B actually do try to change the exact same piece of data at the same time? The CPU cache coherency protocol acts as a referee. If it detects that thread B just modified a memory address that is inside thread A read-write set, a data conflict occurs. The CPU instantly cancels abort threads A transaction. It throws away threads A hidden write set. It rolls. Threads A stayed back exactly where it was before the transaction started. Thread A then takes the fallback path, which usually means giving up on TSX for a moment, just waiting for a traditional boring lock. Do favor of TSX. Hardware lock illusion. This is a backward compatible. Let me sneeze. Okay, so there's two ways to do this. So hardware lock illusion. This is a backward compatible trick. You use traditional lock instruction, but the CPU secretly ignores the lock and tries to run the code as transaction. If it fails, it falls back and actually using the lock. Older CPUs that don't understand HLE just see a normal lock. This gives the RTM. This gives a programmer direct control how to use the new CPU instruction to define exactly where the transaction starts and ends. Write custom code to handle what happens if the transaction aborts. Okay. Oh. This didn't help much, but okay. The rest of it did. All right, that's kind of interesting. So let's do Arch. Let's do x86. Let's do Intel. Fucking hell, that's not what I want. I guess I could just write it in my word. Intel TSX. I had a thing for this, right? I had a way to quickly... Oh yeah, that's the way. Okay, all right. Here we go. All right. Intel TDX enabled by default instead off. Okay. So let's just name it correctly. Okay, Intel transactional synchronization instruction. Fuck. I'm going to write this like garbage. Let me just confirm a quick thing. Okay. Specification describe how the transaction memory is exposed to programmer, but withholds this detail in the actual transactional memory implementation until specifies that its developers are an optimization manual that asks you'll maintain both read sets and write set at the granularity of a cache line. Okay. Okay, Intel's transactional synchronization extension allow for faster lock handling on compatible hardware. It does this by... There's better wording. I'll probably just copy AI for most of it. Assume. Fuck. It was. It does this by assuming the lock won't be already taken. Won't be taken. I guess that's optimistic. Like that's a real name, right? Optimistic execution. It does this by assuming the lock won't be taken. Optimistic execution. And runs the runs the code locally within the core L1 cache. At the end of the execution of the code, it will confirm that the underlying data didn't change. True cache coherency. And will apply the changes atomically in the event where another core modified the underlying memory. If another core modified the memory, the core will roll back the local change and run the code with a standard locking procedure. This change provides for wrong place. I don't have a calculator, so I need to do my math like a fucking retard. Whoops, I reversed it. Provides a substantial performance boost given that the underlying code is uses the instructions. Okay, Intel TSX enabled by default. Auto by default instead of off. Intel Transactional synchronization extension allows for fast lock handling on compatible hardware. It does this by assuming the lock won't be taken, optimistic execution, and runs the code locally within the core's L1 cache. At the end of the execution of the code, it will confirm that the underlying memory didn't change through cache coherency and will apply the change atomically. In the event where another core modified the memory, the core will roll back. The core will roll back the local change and run the code with the standard locking procedure. This change provides a substantial performance boost given that the underlying code uses the instruction. All right. So, nice start. Let's sneeze. All right. So, Intel lands initial preparation for DSA 3 accelerator. Do I care for preparations? I don't care for this. Let's just focus on what is in the kernel and not what's coming up. Unless it's like groundbreaking. Oh shit. Keep Gemini. We'll need it. Oh my fucking god. I couldn't care less about turbostat for real. Like, I'm sure it's a good tool. Should probably look into it in order to give a shit. But goddamn. We're talking about it like 16 times per release. AMD's and 6 performance event and metric merge for Linux. Okay. Fucking ate my nose right now. Oh my god. Ahead of Linux 7.0 merge window closing later today, the Linux 7.0-RC1 release, the perf subsystem tooling change. Okay. Now merge code, add support for Zen 6 event and metric. This include the vendor event handling for Zen 6 core event, on core events, metrics mapping changes. Okay, is Zen 6 something that is like released or no? I guess we could do the like upcoming thing. Upcoming. Perf subsystem added. Perf subsystem added AMD Zen 6 performance and performance event and metrics. And what is this? I guess that's not really interesting. These merge. Fuck, I don't know how to make this exciting. This merge. Okay. The purpose system added AMD Zen 6 performance and event metric. Performance events and metrics. This merge covers performance counter around branch prediction, L1 and L2 cache activity, TLB activity, and more. AMD. AMD's Zen 6 CPUs are set to be released later this year. Later, maybe. All right. I hate misclicks. I hate misclicks. But what the fuck am I gonna do about this? Oh man. All right. We're making some grounds here. We're making some ground. All right, let me go pee. Alright, we're back. Upstream Linux kernel appear largely ready for Intel's next generation Xeon Diamond Rapids. Oh my god. Bro. Is it the character or... Could I have a fucking wiki? Fucking hell. So, you can show something. Fucking AIDS. I'll fucking die. Wiki? No? Guess I roadmap. That must be a meme. Are we memeing? Oh, of course. I need to pay. I guess second half. I love when we're clear. God damn. Okay. Okay. Further prepares for with NTB driver support. What is NTB? Non-transparent bridge handling. Okay. NTB support for Intel Diamond Rapid. With non-transparent bridge, NTB allows multiple I guess it's only with Xeon. Bro, I'm mixing everything right now. Okay. Non-transparent bridge allow multiple systems to share the PCIe. When we say PCIe fabric, what the fuck do we mean? Oh, thank you. Thank you! Nice meme. Okay. Maximizing a PCIe fabric combine all 3 element connect processor, IO device, and to another fabric, connects device through. Flexible cabling, fixed backplate. Oh my god, this is retarded. Give me an image. I guess we just mean some kind of shared PCIe. Okay. And let me say PCI Express because some people are a bit slow. Share the PCI Express. Fabric. Wow. Fabric. With allows multiple systems to share the PCI Express fabric. And allows for fast DMA and shared resources. Is this retarded? Intel's Diamond Rapids CPUs are set to be released later this year. God damn! Okay. We're making like a full-blown like movie out here. What the fuck do we mean by this? Is PCIe 6 the one that we have? Give me a moment. It's 7 that we have now. Fuck. Where did I put this? What? When would I want to open a PDF with Krita? When? Are you fucking kidding me? Oh my god. What the fuck is this? Okay, this is only TDX. Holy shit, I should store my things in ways that I can find them. What the fuck? How retarded am I? Alright. Alright, I got it. I gotta be the bigger retard here. I'm playing a dangerous as fuck game here. I have so many shit that I don't want to share. That are just there. I'm so confused. Okay. What the fuck? It was like half a gig. Can I have my fucking specs? Holy. Why did I put it there? Why? God damn. Sorry. Oh, it's 7. God damn. When you have all of the answers. Okay. Connectivity is what we're searching for? Well, I guess we could just do. Okay. So I guess... God damn. I guess we're talking about this? How can the introduction be so long? Bro, nothing was gain. Nothing was gain. You're going back there. Alright. We're coping. We're coping this, okay? We're not copying, we're coping this. Alright. Let's go. We're bringing this shit down. Performance event. Support. Okay. Um. Oh, fuck. Intel. Also add some perf changes of their own. With Diamond Rapid. Okay, let's do like a quick perf. The subsystem for monitor for monitoring, and there's another word. How can I describe perf? Perf subsystem for monitoring added. Okay, so now we have a little bit of background here. It's a bit more full. Alright, fuck this. Slow workload ends. My nose ain't stopping. Boop, 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 boop. Many power management thermal and ACPI update have been merged. As usual, there are many changes coming from fixes to new hardware support for and more expensive thermal control capabilities under Linux on the power management front. Okay, dropping the old unused TI OMAX CPU frag driver. Okay. Intel idle driver added command line. Okay. Linux will no longer flag the power management workload as feasible to avoid system suspend. Okay. This couldn't be more boring for now. More power to. And by the way, when I say that, this is good. We want boring release, okay? We want them. Base! Was it? Oh, it was. By the number can make CPU The most significant object related to system suspend and hibernation is one to stop freezing the PM runtime work queue during system PM transition, which allows some deadlock to be avoided. Okay, not interesting enough. Alright, fuck this. Okay. Turn on display. Okay. On processors starting from Panther Lake, additional workload type ints are provided. The hardware analyzes workload residencies over an extended period to determine whether the workload classification tends toward idle, battery life state, or sustained performance state. Based on this long-term analysis, it classifies oh my. I don't care. All right. Next up. New long arch CPU feature. All right. We gotta make a long arch thing. Okay. We cannot do without it. Gotta do the long. 2 O's. Not 6. 2. Loon. Long arch. Bro. Okay. Long arch architecture has now SMT at plug support. Hey. Oh. What's the benchmarking on this? God damn. I couldn't have seen a more Chinese BIOS than this. God. That's China. Crazy owl. Like you would expect that it doesn't look like a real PC, but it does. Alright, can we just compare? Fewer is better. Alright. I think that's not a fair comparison, but... Whoa! What the fuck's up with that? Do we got other wins, or... is it getting trounced everywhere? But there. Oh. What the fuck is this? Checking. Quicksilver. Do we have a comment about this? Benchmark. Quicksilver. Okay. And what does it test? God damn it! Alright, fuck me. Like, mercury workload. Holy shit, I have no idea what the fuck this means. Alright. Let's just check current pricing. What the fuck is this? Nose. God. That one hurts. All right. Well, I guess we need to compare, right? Oh, I'm getting fucking doxed. Like, are they still being sold or? Fuck. I don't know. Nope. That's the most retarded shit I've written all day. Okay. God, that's old. I haven't kept up with the gens, but... Okay. Okay, so let's say 250 for... I like the docks, holy fuck. Okay, 250 for the CPU. Oh. Well, we have something that shows here. And we have... Okay. That's not the right gen. Fucking Amazon. I think that's the right gen. I don't want to check. What was the other one? 7. Oh, it may not be. Okay. B 860. Okay. All right. Okay, so the bang TLDR, bang for your buck. It ain't here. It ain't here. I just want to see again. What's the lowest CPU that was on there? Oh well. Well then I may need to compare to a Ryzen 5. Fuck. And it's which version? 960X. Okay. So 230, and the boards will probably be cheap as hell. Okay. TLDR, bang for your buck, ain't here. Ain't here. Wait. Am I being retarded? It won't allow me to. Oh, okay, there's a new shopper thing. So we can assume $600. Okay, $600 can for the board plus CPU plus cooler per dollar can be found on x86 AMD and Intel. Okay. So the benchmark shows Long Arch is making some progress with their chips, even matching some x86 CPU in some benchmark. But let's not get ahead of ourselves as the comparer as this CPUs compared didn't have the same core count. Still impressive gain that will surely be useful on the Chinese market. Chinese with a capital. Okay, the benchmark shows that Long Arch is making some progress with the chip. Okay, good. And let's okay. Do I want to talk about anything else Long Arch related? When we say SMT, okay, we're going to focus on the bench here. Improvement continues to the Chinese architecture. The benchmark shows that Long Arch is making some progress with their chips, even matching some x86 CPUs in some benchmarks. But let's not get ahead of ourselves as the CPUs Let's make it capitalized. CPUs compared didn't have the same core count. Still, impressive gain. Impressive gain that will surely be useful on the Chinese market. $600 Canadian. Canadian for the board. CPU cooler. Better perf can be found on the at a price of okay. Pause. We pause for finances. TD, where are you? TD, my boy. TD. We going the fuck up. Alright. That's all good. I'm having fun here. Okay, I think I've quoted everything. Right. LPSS. Okay. Whoop. I'm having some freezes. That's another don't know, don't care. Oh, man. If I need to do like 15 minutes of explaining for something to go, it ain't going. And when is Nova Lake coming in? Is it something that's already out? Okay. Diamond Rapid. Server CPU. Okay. So Intel Nova Lake is... Fuck, I don't know how to say it. It's not enthusiast. Not prosumer, not consumer. Well, I guess it's consumer. I guess desktop's it. Okay, for Intel Nova Lake, which is a desktop slash mobile platform, we have, and they're going to talk about sound, I guess. Okay, when we say Linux SOF driver, it's an open firmware. Fuck, misclick. We have for Intel Nova Lake, which is a desktop and mobile platform. We have sound support. True. No T. D. Linux. Sound. Open. Firmware. That was added. Alright, they're all fucking dude for this. Alright. They're all going to be there soon. End of year. Alright. So that's fun. CXL. Okay. I'm thinking about compute expressing. Okay, okay. Yeah. Just wanted to be sure that it wasn't like, oh no, it's CLX, something else. Okay. Long in development feature for AMD EPYC Zen 5. Okay, so the current, right? Zen 5 platform is the one we have. Yeah, current. Okay. Fuck. All right. A long in development feature for AMD EPYC Zen 5 server platform now merged in Linux 7.0. Kernel is ACPI PRMT based address translation for, god damn, those are some acronyms. I have a page for ACPI, right? God. Fuck, you're telling me I don't have this one? PRMT. Ah. Okay. Fuck. My brain in there. Just give me half a second. Need to go pee. Alright, I'm back. Okay. So PRMT based address translation for Compute Express link. I don't know which one I want to read first because I'm a bit confused about what the fuck it does. Coffee really makes me pee. God damn. Okay, Zen 5 system may be configured to use normalized addresses, then host physical address, are different from their system physical address. Okay, I'm a bit confused. The endpoint has its own physical address space, and an incoming HPA is already converted. HPA is host physical address is already converted to the device physical address. Thus, it has interleaving disabled and CXL endpoints are program pass-through. Okay. Host physical addresses, HPA, need to be translated from endpoint to its CXL host bridge. ESP is especially to identify the endpoint root decoder and region's address range. ACPI platform runtime mechanism provides a handler to translate DPA to its SPA. With normalized addressing, this PRM handler must be used to translate an HPA of an endpoint to an SPA. Okay. Do the following to implement Zen 3 addressing. God damn. Okay. The problem is I have no fucking idea how CXL works. Like, can we have a wiki on this? What? Fuck. Can I have a clean image? Cute. But that ain't helping. Oh man, I'll need to reread this like 15 times. Okay, first of all, let's define this. Bro. You know it's bad when kernel config comes first. Okay. Background on system management mode, SSM, so that's the like giga super mode, god mode that you can set your CPU and you can do anything from. is an operating mode in x86 computer architecture. SMM mode is written within the context of a software firmware and is typically used for system-wide function, which are highly platform and silicon specific. Yes. Some example would be RAS, so errors, power management, execution of OEM proprietary code, platform hardware event, and implementation of hardware workaround. In order to enter SMM, the system management interrupt must be generated, by the platform event. SMI is a high priority, non-maskable broadcast interrupt. On receipt of this interrupt, the processor in the system saved error context is in SMRAM. What do we mean by SMRAM? System Management RAM? I guess so. No definition. In SMRAM and transition to SMM to execute the corresponding SMI handler to a given event. The SMI handler code then sets up its own environment, page table, IDTs, interrupt, something table, right? IDT are to handle interrupts. Fuck. Man. Interrupt descriptor table. All right. Identifies the source of SMI and handles that event accordingly. The SMI handler is placed by the platform BIOS during boot in a special area of memory called System Management RAM. Ah, okay, we got it. System Management RAM is invisible to OS VMM. A processor executing in the 0 to 3 ring privileges level will not be able to read from or write to SMRAM space. I should say the full acronym each time. When the processor switched to system management mode on receipt of a system management interrupt, then processor execute code out of system management RAM area. There are two different categories of system management interrupt sources, asynchronous and synchronous. System management interrupt, due to the platform and hardware events, are asynchronous in nature. Software system management interrupt are invoked by writing to port 0xB2, so the Intel architecture platform, and are synchronous in nature. The document describes the platform runtime mechanism as a means to remove the usage of certain classes of SMI handler, PRM, along with native OS driver offload to other hardware engines such as baseboard management controller, offer a path to eliminate runtime SMI. Okay. So I get the issue that we're SMI is garbage. What's the link with ACPI? Am I at the right place? Am I lost? Okay. Advanced Configuration and Power Interface, ACPI, is an open standard that defines a mechanism for the operating system to discover and configure hardware component and actively perform device and platform power management. ACPI code is written in the ACPI source language, ASL, not what is ASL? Sign language, okay. American Sign Language. I don't know why. Which one did I add in mine? It fits with that picture. American Vernacular English. AVE. No. Okay, we're not doing that meme. We're not doing that meme. That's racist. Okay. And typically shipped as a binary component in the form of a bytecode called ACPI Machine Language in the platform firmware. Okay. Today's ACPI firmware serve as a conduit to SSM by sometimes triggering an SMI to invoke some platform-specific functionality. Okay. In conclusion, SMI is a very powerful mechanism for invoking runtime platform interface that has complete access to system memory and system hardware resources. SMI enables a large number of technologies to be employed in scenarios where the system software is unavailable. For example, during an OS operating system has crashed for error harvesting, or it's just written weirdly, or on AC power failure to ensure data persistence for non-volatile DIMMs. Okay. Through this power comes some notable downside: unpredictable performance jitters, as all threads in the system are stalled for simple error collection, for example, corner case and race conditions such as SMI merge out of sync SMI and OS kernel panics. There is a massive industry-wide push to move away or reduce SMM, system management mode footprint. The goal of this document is to provide mechanism to reduce and eventually eliminate system management mode usage that result in unpredictable performance jitter in the platform in OS runtime. There could still be a usage model based on planned SMI event or SMI event during end of life of boot, but those don't give rise to unpredictable performance impact and is out of scope of this specification. SMM usage. God dang, we're getting deep in this. Can I understand if I'm reading the right thing? Fucking hell. I think we'll skip there. Platform runtime mechanism overview. Platform runtime mechanism introduces the capability of transitioning certain usage that were hitherto executed out of SMM to a code that execute with the OS VMM context. Such usage are those that don't require SMM. Fucking hell. Wording that we don't understand now. Goddamn, goddamn, goddamn. Okay, so they're just talking about that part that they believe that they can, like, embed, I guess. Fuck. Yeah, category 1, and a subset of hardware and SMI handler that don't require SMM privilege. Category 2, this eliminates many of the cons present when executing some code within the SMM environment. The code can also be updated within the Ring 0 software environment through targeted online servicing of specific sets of functionalities. As shown in the figure below, 3-1, we'll see what it looks like in a quick moment. Platform runtime mechanism provides an ACPI interpreter-based infrastructure to invoke runtime platform firmware handlers. These runtime handlers are called PRM handlers and are placed by the BIOS during boot and updatable in OS runtime in a runtime area reserved for firmware usage, such as UEFI runtime area. Note, the ACPI interpreter-based PRM infrastructure is the PRM operation region handler in ACPI subsystem and can also logically be implemented as an independent driver, bridge driver, in certain implementation. This specification interchangeably uses the term bridge driver, PRM OP region handler, ACPI driver, ACPI interpreter, or ACPI-CA. God damn. Choose a fucking name to mean the same thing. Fucking hell. Okay. PRM handler can be invoked by two means. Directly from an OS driver, if the OS driver and the OS ACPI subsystem is PRM aware. From ASL context, if the OS driver is not PRM aware and uses _DSM instead of platform event to trigger an SCI. What the fuck do we mean by SCI? Generating SCI. I love when we have to like skip one small thing and it's like, okay, we don't understand anything anymore. I'll fucking regret not reading this. Holy shit. ACI. No, it's SCI. SCI. System control interrupt. Okay. Okay. PRM overview. OS driver invoking through ACPI. ASL method. OS driver invoking ACPI driver. PRM handler. Okay. PRM requirements. This Canadian motherfucker always streams when I'm at work. Savinic already made several Linux 7 vids. I know, he's stealing the format, okay? That motherfucker. He's pushing things out while the kernel is not even out. Fucking bitch. No, I think he makes this full time, right? Like, doesn't he put out pretty often? I mean, good for him. He has a big channel. He makes a bunch of views. So, that's good for him. Alright. PRM handlers must be capable. Must be code capable. What the fuck? PRM handler loaded at boot time should be part of the firmware boot chain trust. Okay, I'm not going to understand any of that. Fucking hell. Okay. The PRM T-table is an ACPI table published by the BIOS during boot, which advertises the pointers to the PRM handlers. That's not the thing that's in there, right? Oh, fuck. What? So... Have you seen new tutorial how to install Linux? No, I have not, and I don't need to. Okay, I think I'm reading all of this for nothing. Fucking hell. You have to watch. Well, which one it is it? Brody. Oh, for fuck's sake. Now I have to watch. But it's the only interruption, okay? Whoops. Alright, that wasn't it. Brody. What's his name? Linux. Oh, it's Robertson. Oh no. Oh no. Oh, okay. It's an April Fool's. Is that the meme? By the way, this song has a copyright. um, is this all like a meme? What a fucking waste of my time. God damn. Nice April Fools, fucker. It's real, you get Ubuntu. Cool! Okay. Okay, what the fuck do we mean by normalized address on Zen 5? That's probably the thing that I need to understand. AI, help me. The Zen 5 includes a feature that provides normalized address for a device attached to the data fabric, such as a memory controller, I/O device. These devices may not have a complete view of the system physical memory and report memory error address through machine check banks in the form of UMC relative normalized address. Normalized address must be translated to system physical address for the kernel to take action on the memory. And what's the fucking point of this? Fucking hell, I love when there's a feature and it's like, why does it exist? It exists. Manage the layout of physical memory. That fabric may not have a complete view. Holy fuck it. The AI just copy pasted. I fucking hate it. These devices may provide a normalized. Okay. What's the point? Okay. Why is then defining the queries focused? I'm pissed. That's the queries focused. Understanding data fabric. Oh, you got it, bitch. I like how I have. I don't even know what the fuck that means. Oh, fuck. How can that be? Is that the Rust binaries? Oh no. Really? That's kind of big. For the same thing? At its core, the concept of normalized address exists because how AMD's modern chiplet architecture handles memory routing and interleaving. While this concept exists since earlier Zen generation, it has become heavily documented in structures around the Zen 5 due to the introduction of CXL and consolidation of the Linux kernel subsystem. Here's a technical breakdown of why this feature is absolutely necessary: system physical versus device physical. To the CPU cores and operating system, memory looks like one giant continuous flat map. This global view is the system physical address. However, physically, RAM is not one continuous block. It is distributed across multiple memory channels managed by different unified memory controllers. To maximize the memory bandwidth, AMD's data fabric interleaves stripes the memory across those controllers. For example, if you have two memory controllers, the data fabric might send the first 64 bytes of memory to UMC0 and the next 64 byte to UMC1 and the next to UMC0 and so on. Because of this interleaving, the individual UMC has no idea where its attached RAM fits into the global SPA space. It only knows its own local continuous view of memory directly managed. This local controller relative address is normalized address. Oh. The problem, hardware errors. Oh, okay. Okay. Okay, now that makes sense. New core util, yes. Isn't that a bit bad? Like, I don't care about space. But when we're talking about, like, 1000x growth, that's, well, it's not 1000x, it's, 200x, but, like, it's still pretty big. Or, like, is there really an advantage? Is it faster? Is it? Okay. Alright, so I guess we can explain this. Fuck doing the documentation correctly. Okay. Okay. Let's do the Intel thingy. AMD thingy, I mean, AMD. So, AMD is in 5. Faster in some cases, slower in other. Hold on, I'm testing. God damn. That's a nerd thing to say. I'm benching as we speak. Okay. Zen 5. Systems can be configured to use normalized address. Normalized address says, do we put an S on there? Yep. These normalized addresses will be this feature will create two types of address. Fuck. I'm misunderstanding this. I need to reread it. Or maybe I need to read it on the actual fucking patch, okay? Oh man, there's not going to be more detail. Okay. Zen 5 system may be configured to use normalized address. Then the host physical address are different from their system physical address. Okay. The endpoint has its own physical address space, and an incoming HPA, host physical address, is already converted to the device physical address. Okay. Thus, it has interleaving disabled, and CXL endpoints are programmed pass-through. Okay. Host physical address needs to be translated from the endpoint to its CXL host bridge, especially to identify the endpoint's root. Fucking hell. Root decoder and region address range. I'm so confused. With normalized addressing, this PRM must be used to translate the HPA to its endpoint of an endpoint to its SPA. I don't know which is which. Which is the one used by the device and which is the... Okay, so I guess host physical address is the core, what the RAM would be on the main thing, on the CPU, and system physical address would be the system specific, like we're talking about CXL endpoint would have their own SPA. Fucking hell. Okay, they didn't replace all utils yet. That was my understanding for Ubuntu. They didn't pull the trigger everywhere. When normalized... Okay, so SPA is for the endpoint, and HPA is like the host. Okay. Fuck. Identify the region entirely and word blank. Okay, I think I get it. But what the fuck? I CP'd several times and it got faster. Well, wouldn't this be expected? If you do something several times, it's going to be cached? No? Like, I'm not talking about the item that you're transferring, if you're transferring from, like, random, but I'm talking about the code itself. Anyway, this feature will... It can be configured to use a normalized address. Okay. This feature creates a split between the addresses of the CXL endpoint, which is the system physical address, and the hosts. The address space. Can I say as seen from the CPU? I guess. This feels a little bit like... So I'll get lit the fuck out if I say this out loud. Okay. Okay. Let's reread this and target where we want to go. AMD Zen 5 address translation enabled for use with CXL. Zen 5 system can be configured to use normalized addresses. This features create a split between the addresses of the CXL endpoint, system physical addresses, and the host physical address, HPA. The split allows the host to stripe the split allows the host to stripe the memory along multiple physical devices. The AI was saying it in a better way. Allows the host to interleave the memory along multiple physical devices. Did I invert it? Fuck. Let's reread this. To the CPU cores and the operating system, memory looks like one giant continuous flat map. Hello, MB. Yes, we're cultists. Flat map. This global view is the system physical address space. However, the RAM is not one continuous block. It is distributed along multiple memory channels managed by different unified memory controllers to maximize. I think its wording is fucked here. Oh, 12 megabyte is all utils in one, like BusyBox. That makes sense. But the size is still a little bit beefy, no? I don't know, we should have like a comparison. Fuck, I'm misunderstanding all of this. MB, do you want to help me? Okay. I'm trying to understand. If you're able to. I've read like this 15 times. I'm having a hard time understanding the difference between host physical address and system physical address. So here's what I know like for sure. So we have a full address map. That's like the CPU view of everything. So your system like sees everything, all the memory as a value. And then there's like a device specific. So if you have like multiple CXL endpoint, or like your system RAM, or like another CXL endpoint, they will have like their own little address space. But I don't know which is which. Which is the big one and which is the like device level. And when I say device, I mean like CXL endpoint level. I don't understand. Like my brain breaks down when I read this. So I'll just go P because I fucking... Even the AI is fucking me here. Like it's not being precise. It's funny because it has several 12 MB files just because the binary knows what command to execute based on the file name. Okay, so they really just like they copied the file instead of doing references to it. Are you sure that... Oh, something that you can see, Rust. Is it a hard link? Because symlinks will show in like when you go inside of your files, but hard links won't. So maybe they're all hard links, so they're all the same file. Like if you're actually on an interface, the way that you do that is you select multiple of those files and you check their size. If their size is still 12 megabytes, even when you select multiple together, you'll know that it's hard links. Anyway, give me half a second, I need to pee. What do you mean by Didn't you understand my explanation? Don't you know the difference between a symlink and an hard link? So, oh man. I don't want to yap too much, because if MB is checking into it, that's good. I'll just check. I'll need more time to catch up to you. Okay. That's all good. That's all good. I'll fucking figure it out. Oh, I guess it's explained here. Ooh. You can yap. I can yap. Yeah. Okay. CXL fixed memory window structure. Describe. Oh, maybe this will give me a full fucking view of the thing. It will! If I go and I do like Linux documentation, this, it will give it to me, right? When we do latest, okay, it's based on this, good. Oh, it's hardling then. Boom! Oh god. Giga brain! This also means that... Oh, wait. Wait, does that mean that if you install Ubuntu on a file system that doesn't support hardlink, it would break? I wonder if they thought about that. I don't even know which FS doesn't support them, but that would be a fun one. Okay. Let's yap. The CXL fixed memory window structure, CFMWS, goddamn, describe the 0 or more host physical address, Windows. Oh, okay, so we have our answers, I think. Associated with one or more CXL host bridge. Each HPA range of a CXL host bridge is represented by a CFM tree. In the an HPA range may include, I should just say it in full, the host physical address range may include addresses currently assigned to CXL.mem devices, or an OS may assign a range from an address window to a device. An host-managed device memory is a device-attached memory that is mapped to system-coherent address space and accessible to the host using standard write-back semantics. The manage address range is configured in the CXL HDM. Am I supposed to know what the fuck this is? Decoder register of the device. An HDM decoder is a device responsible for converting HPA into DPA by stripping off specific address bit. Okay, MB, I need to make you catch up. So TLDR, okay? That's what a bit more about what I know. The reason why... Fuck. Okay. This is true for A, M, D, Zen... That's how we do a Z, right? Zen 5. Okay, that's a bit too much. 5. Okay, so AMD Zen 5. It has like a main address. I guess we would call it system physical address, I think. Anyway, you have a main address space like you normally would with your system. And then you have like, let's say multiple CXL device that are essentially just RAM banks. So you have these CXL device. Let's just assume that they're RAM. So in order to improve performance, instead of mapping them one-to-one like this to your RAM, what you want to do is you want to interleave them. So you want like the first 64 bytes to be this one, the next 64 bytes to be this one, the next 64 bytes, you get it, right? So you interleave all of them in order to like have them two map together and get better throughput. So the whole idea of this is to get that better throughput. So that's what we're reading about. Yeah, I'll try to like yap more about what I know so that we can both get an understanding. Okay. So the coder. Here I'm like not quite understanding the stripping off part. Well. Oh, maybe it would make sense when they say stripping off. If you say every 64 byte, like I don't remember the positioning of things. So this is the 1 position, 2 position, 4 position, 8 position, 16 position, 32 position, and 64 position. God damn, this is targeted. So you would essentially look at your address, look here, and depending on what value you have here, you would go to CXL1 or to CXL2, right? So when they say stripping off address bits, I guess this is what they're referring to. Anyway. Or maybe we're not there yet and we're like reading something else. CXL device and CXL bridge use the same HPA space. It's common across all components that belong to the same host domain. The view of the address region must be consistent on the CXL length path between host and devices. So would they use a bit mask to create the interleaving? That's kind of my understanding. Well, no, they would just need to, I don't know if that's what you mean by bit mask, but they would just have to do like an if statement, the equivalent of an if, on a specific bit position. And then you throw something to one side or something to another. Maybe I'm too retarded to see how this would be like complicated, but depending on the interconnect architecture of the platform, components attached to the host may not share the same host physical address space. Those platforms need address translation to convert an HPA between host physical address between the host and the attached component, such as a CXL device. The translation mechanism is host specific and implementation dependent. For example, x86 AMD platform use data fabric that manage access to physical memory. Devices have their own memory space and can be configured to use normalized addresses different from the system physical address space. Address space translation is needed for detail. What isn't that what I'm fucking reading here? Oh no, that's the thing that doesn't tell us fucking anything. Zen-based AMD includes data fabric that manage the layout of physical memory. Devices attached to the fabric, like memory controllers, I/O, etc., may not have a complete view of the system physical memory map. These devices may provide a normalized, i.e. device physical address when reporting the memory errors. Normalized address must be translated into system physical address for the kernel too. Oh, okay. System physical. Am I like switching back and forth on these? System physical. Fucking hell. System physical would be what the... No, this doesn't make any fucking sense. God damn. I'm confused. Those AMD platform provides PRM handlers and firmware to perform various types of address translation, including for CXL endpoints. So, okay, when they say PRM handlers, what they mean is that ACPI has this standard. So ACPI have what we call PRM handlers and these PRM handlers, what they do is they provide pointers to like little programs that you can run to do a thing. So this is normally something that exists because we want to avoid the what's his name? Secured management mode. You know, the like super root, goddamn, the super root level of the CPU secured management mode. I'm pretty sure that's I'm unsure about the S. Yes, it's secured management mode. I'm pretty sure. So secured management mode, we want to avoid it. So instead of using this like magical system in order to do shit, we have this PRM table that contains all of those pointers to specific small programs that we can handle using the kernel to do things. So right now the things that we're using these little programs to do is to like get an address from something, I guess. Fuck. My wording is as good as it will get. Okay. Those AMD shortcut vector table. I don't even fucking know what a vector table is. Interrupt vector table. Okay. So essentially, if this do this, yeah. Okay. Yeah, I think I get it a bit. Just a bit. Okay. Those AMD platforms provide PRM handlers in firmware to perform various types of address translation, including for CXL endpoints. AMD's N5 systems implement the ACPI PRM CXL address translation firmware call. The ACPI PRM handlers has a specific GUID to uniquely identify platforms with support for normalized addressing. This documented in ACPI. When in normalized address mode, HDM decoder address ranges must be configured and handled differently. Hardware addresses used in HDM decoder configuration of an endpoint are not SPA and need to be translated from the address range of the endpoint to that of the CXL OS bridge. Aren't those the same thing? Oh, I guess I'll see here. This will help, okay? This will help. Hope. This is especially important for finding the endpoint associated CXL OS bridge and HPA window described in CFMWS. Additionally, the interleave decoding is done by the data fabric, and the endpoint does not perform decoding when converting HPA to DPA. Oh, I guess when they say endpoint, they mean like endpoint. Oh, okay. I get it now. I get it. I'm big brain. Okay, I'm big brain. Let's reread this. Additionally, the interleave decoding is done by the data fabric, and the endpoint does not perform decoding when converting HPA to DPA. And when we say DPA, we mean device, physical address, and here we mean host, physical address. Okay, but what the fuck does this... What does SPA go in there? Man. This is LLM generated. How the fuck do you know this? I think it's the reverse, no? This is not LLM generated. This is what the LLM reads to generate something because it's the only value that exists. Is it written somewhere? No, then shut the fuck up. Instead, interleaving is switched off for endpoint one way. Finally, address translation might also be needed to inspect the endpoint hardware addresses, such as during profiling, tracing, or error handling. This is hard stuff to try to understand. First thing, when I wake up, I need my meds, caffeine, and to wake the brain faster, brother. I'm trashing myself. Look, we're making some progress here, okay? We're making progress. We're here, okay? We're doing great. That's how we gotta feel about this. But it's interesting. Keep going. Yes. Okay, but who makes ASCII? Everybody makes ASCII like that? What the fuck's your point? This is like a thing that has existed since the end of time. Anyway. Okay, let's... Instead... Fuck. Okay, so the endpoint does not have to do any decoding. We got it. Finally, address translation might also be needed to inspect... Okay, so we need address translation... Okay, I think I get it. For example, with normalized addressing, the HGM or look at photo. Okay, so root decoder, so that's our system, right? Then host bridge decoder, that's the CXL bridge thingy. And then we have our endpoints. Okay, so the endpoints themselves don't do any decoding. They receive their instruction like directly from big boy CXL bitch. And CXL bitch, it will, I guess, it will interleave all of those together. DPA device. Okay, so they each have their own device address. And I guess here, if we were to read enough, we would see system specific address. Okay. So SPA. And where is H whatever? HPA? Host physical address? God damn. Okay, SPA. Where is SPA? System physical address. Okay, I think I get it. I think I get it. Let's write it here, okay? Let's scroll up. Each of those have small device physical addresses of their own. Device physical addresses, okay? And then this, where did they write it? This is technically a system physical address of itself, because this is a whole system. This whole thing is a system, right? And then the system physical address is itself mapped onto the host physical address, which might encompass like some other memory module or some other, well, some other system physical address, technically system physical address, right? Okay. So host is the big one, system is the CXL part of things, and device is the individual chunk of memory. Okay. You're on a wave. I'm on a wave. We have been making these when I started programming in the 70s. Based. Someone made a test recently where you have to guess which text was written by a human. Okay, and you probably fail it every time. I love you, Rust. Okay, I love you. You would probably... you would be the type of person that would look at my fucking graphs that I made and you would say AI. That's you, okay? That's you in the chat. Being there. He made it with AI! No, I wasted a fucking month on this, okay? That's how it works. Okay. So yeah, we have some granularity here. And they have like their own individual address space. Their device physical address. You know what's bad about this? Is I'll fuck this up. And everybody will rage at me in the comments and say that I'm a retard. While 99% of things will be perfect. I fucking hate this. Is this a protocol for multi-CPU installation or VM or better DMA? It's to use CXL, so the what's the name? Fuck. Compute Express link with multiple storage device. That's all. With AMD. This is AMD specific. Okay, allow CXL device to be an HPA space other than the host. Okay, CXL support for multiple CPU share memory. I am retarded. There's no multiple CPU sharing memory here. That's not important. So here, the goal of this is just better performance using CXL in order to connect multiple RAM banks. Because unless I'm the retard, the AMD fabric, like the data fabric of AMD, if we go and check AMD data fabric, memory handling, if we go and check this, they will probably say we're stripping all the data and interleaving everything in order to get more performance. It's probably like the thing they do. Okay, so that's just a counter. Can I... Fuck. Maybe it's too boring. I'm not sure I understand your last comment, but okay. Here it is. We're not talking about VMs and all of that shit. We're just talking about having some interleaved memory. That's all this is for better performance using CXL. No multi-VM, no... Like maybe it can be used in that way, but that's not the goal here. Oh, benefit of the change. Without the change, the operating system may be unable to determine the memory region and root decoder for an endpoint. Its corresponding HDM decoder. Region creation would fail. Platform with a different interconnect architecture would fail to set up and use CXL. Huh? Keep going, you're where you're going. I'll catch up before you publish the video. You're not that back, okay? Not that back. I think we're gonna have to read this a bit more, but... Without the change, the operating system may be unable to determine the memory region and root decoder for an endpoint. And its corresponding HDM decoder. What a strange way to say it wouldn't fucking work because it would have no idea where things are. But here I'm a bit confused. Does that mean that this would work outside of AMD? No, because we would need the PRMs. Well, the PRMs exist outside of AMD, but they probably are not set up in the same way, so they couldn't be used. Because PRM is like something that is firmly given by the firmware. Well, most times. Fuck. Not firmly then. Okay. CXL IDM okay. A device may use an HPA space. So HPA is the middle part. HPA is this. No. No. HPA is this. Right? We have this. We have this. And we have this. HPA is this one. Host physical address is the biggest one. Okay, biggest one is host physical address. Oh, yes, but they're retarded. Okay, let me yap a bit more. The problem is this, okay? So the CXL, when they manage it, inside of it, the way that it's written, they write HPA to talk about SPA. So this is why they word it like that here. Allow CXL device to be in an HPA space other than the host address space. Is because when they say an HPA space other than the host address space, they mean to be inside of SPA. But CXL, the way that CXL is written, they probably only talk about HPA because they didn't foresee that you would do this shit. God damn. Rust, what do you mean by founded? Go ahead, my friend. Go ahead, yap. Okay, a device may use HPA space that is not common to other components of the host domain. Okay, so may use an SPA. In my mind, those things were handled by the BIOS firmware level. I guess I wasn't in the right mindset. So, MB, it depends what you mean by handle at the BIOS and firmware level. My understanding right now is that... Fuck. This guy will do most of the decoding. Like, it will do everything itself. But whenever you want to, like, have an error or pinpoint something specific without, like, asking the bridge to do it, you need to go ask your PRM handlers, which are technically BIOS and firmware thing, because they're part of the ACPI standard. So you're not far from it, right? So if I have if I need to debug something, if I get an error from one of these, I'll need to call this to decrypt whatever error I'm getting, because the endpoint has no fucking clue what memory address like are globally, and even this one technically has no clue what memory address are globally, because it only knows its SPA. It doesn't know the HPA. So it doesn't know the host physical address, it only knows the system physical address. No, I'm addressing it because I don't want to be a retard. This was easy for me. Okay, okay, we're doing it. Refactoring English. Can you swap the human version? Okay. Okay, there's a bit too much emoji. Well... Okay, so I need to disregard the top thing, I guess. For now, C looks like shit. So I'm assuming that it's the one. Okay, C looks like shit. Yeah, I would have said that this one is AI. I don't get it. Why the fuck did you put emoji? Why would you do this? Okay. And what does this prove? Failed basic AI tests. Okay. Bro, it's just too good, I guess. Too good at looking human. Okay. A device may use HPA space that is not common to other component of the host domain. The platform... Oh, okay, so here they're referencing the specification. Okay, cool. The platform is responsible for address translation when crossing the HPA spaces. The operating system must determine the interleaving configuration and perform address translation to the HPA ranges of the HDM decoder as needed. The translation mechanism is host-specific and implementation-dependent. The platform indicates support of independent HPA space and the need for address translation by providing a platform runtime mechanism handler. The OS shall use that handler to perform necessary translation from the DPA space to the HPA space. The handler is defined. Session, okay. PRM handler for... Okay, let's read this. PRM handler for CXL DPA to system physical address translation. A platform may be configured to use normalized addresses. Host physical address space are component specific and differ from the system physical addresses. The endpoint has its own physical address space. All requests presented to the device already use device physical addresses. The CXL endpoint decoders have interleave disable, one-way interleave, and the device does not perform HPA decoding to determine a DPA. The platform provides DPA handler for CXL DPA translation. The PRM handler translate device physical address to system physical address space, to system physical address for specific CXL endpoint in the address space of the host. SPA and HPA are equivalent. I need to reread this. The platform provides a PRM handler for CXL DPA to system physical address translation. The PRM handler translates a device physical address, so that's the endpoint, so that's the specific like memory module. Okay, so device physical address for a specific endpoint. In the address space of the host, SPA and HPA are equivalent. And the OS shall use this handler to determine the HPA that corresponds to a device address. For example, when configuring HDM decoders on platform with normalized addressing, the GUID and the parameters buffer format of the handlers are specified in section. Okay. If the OS identifies the PRM handler, the platform support normalized addressing, the OS must perform DPA address translation as needed. Fuck, I feel like they could have juiced so much information from that, but it was so underwhelming. Like, all they said is, brother, if you get something from a DPA, you need to translate it. But I felt like they were like maybe spitting here. Okay, and here they say how to call the PRM. Okay, now my issue is... Okay. What I need to understand is... Let's do blocks. DPA, HPA, SPA. Okay. The address here, is it 0? Or is it like already something? Right? Like, is this 0? Like, this is 0. But inside of SPA, when we look at the address, does it reset back to 0? Like as a separate address space? Or is it directly bind to the host address space? I guess that's what the range means? Can I have X somewhere? Oh, bro. I like it when exactly what I want. Okay. It's not what I want. Okay. Decimal. Not the full thing, just this. So decimal to X. So the number I guess it's the GB byte thing, maybe? Nope. Okay. So when they say SPA range, they mean starting range. So it would have, like in our example, we don't start at 0 within the main block. So we truly start where we are, not at 0. Okay. I think there's something that talks about it here. Wrong thing. Oh, fuck, this is... We're back in mixing me the fuck up. All right. Zen5 system may be configured to use normalized addresses. Then host physical addresses are different from their system physical address. The endpoint has its own physical address space, and an incoming HPA is already converted to the device physical address, DPA. Thus, it has interleaves disable in CXL endpoint or program pass-through. Okay, so we can disregard whatever the fuck this is. This is just there to confuse us. Host physical address need to be translated from the endpoint to its CXL host bridge, especially to identify the endpoint's root decoder and region's address range. So within an SPA, we need to know, like they say HPAs, but they should say SPA. It's just because CXL doesn't have a concept for what SPA is, I guess. Okay, a CPI runtime platform provides an handler to translate the DPA to its SPA. I'm just scared that I'm fucking up what SPA is, but it doesn't make sense with this, right? Not this. Like, why would this be here? Or is the range within the SPA? SHPA. What the fuck? SPA. What do you mean? Spa. If you're trolling Rust, this is not the time. What the fuck do you mean with this? I have no fucking idea what you're talking about, okay? Okay, fuck you. Okay, nobody is going to have a fucking answer for this. Because here they could mean the range within the SPA. So that would mean that SPA, it would mean that I fucking inverted it all, right? It would mean that this is actually SPA, that this is always HDA, and that this This, of course, is always DPA. I think I inverted it. When in normalized address mode, HDM decoder address range must be configured and handled differently. Hardware addresses used in the HDM decoder configuration of an endpoint are not SPA and need to be translated from the address range of the endpoint to that of the CXL host bridge. This is especially important in finding, okay. Okay. CXL decode. With PRM calls, kernel can determine the following mapping. Okay. Okay. So SPA is the whole system. HPA is like, I mean, when they say host, they mean it's host bridge. Okay, I inverted it. This answers it. Fucking hell. The benefit of this split is the ability to interleave your memory across multiple CXL endpoint, allowing for better performance. Okay, so let's just make a dumb little diagram. So we have SPA, whole system mem. And here can say system. Where do we say? Fuck. Nope. How can I do a downward arrow? I guess I can go download it. Oh, maybe it's in here? Thank you. Yeah, maybe tabulation are the way to go. In this system, the CXL endpoint doesn't manage any of the fuck. Da-da-da. Yeah. In this system, the CXL endpoint doesn't know about HPA or SPA. It operates off the instructions given by the CXL host, which translate and relieves the data okay. In the system, the CXL endpoint doesn't know about HPA or SPA. It operates off the instruction given by the CXL host, which translate and interleaves the memory addresses. The HPA also doesn't equal the an HPA address. An HPA also doesn't equal an SPA. I should an host physical address also doesn't equal all of this means that we may need to translate, no, that we will need to translate one address space to another. The way that we achieve this how do we write achieve? Oh, okay. To achieve this, we use a CPI, and it's PRM, right? What's the real name for PRM? Whoops. To achieve this, we use ACPI, Platform Runtime Mechanism, PRM, handlers. These small programs are created in a we probably have it at the top. ASL. What does ASL mean in this? Fuck. Okay, it's fucking me. Nice one. Nice one! We're getting too deep in this. These programs are created. No, it's not too deep. It's not too deep. These small programs are created in ACPI source language, ASL. Okay, now my understanding is that the CXL can directly get these programs, and it even uses it for its... Bro, what the fuck? For its own, like, use case. Like here. A device may use HPA space that is not common to the other component of the host domain. The platform is responsible for the address translation when crossing HPA spaces. So here, when they say HPA spaces, what they really mean is SPA to HPA. It's just that SPA is not something that exists in CXL. The operating system... Well, maybe I'm retarded, but who gives a fuck? I'm fucking rolling, bro. The operating system must determine the interleaving configuration and perform address translation to the HPA ranges of the HDM decoder as needed. Okay. The translation mechanism is O-specific and implementation dependent. The platform indicates supports of independent HPA spaces and needs, and the need for addressing translation is provided by platform runtime mechanism handler. The OS shall use that handler to perform necessary translation from DPA space to the HPA space. Okay. Oh, it's that part. A platform may be configured to be used normalized. The physical address space are component specific and differ from system physical address space. Oh, okay, I think I get this now. So this essentially means if you have multiple computers on your... Well, maybe it doesn't mean that directly. But if you have multiple computers connected to your CXL, it means that the CXL itself has no concept of what SPA you are on. So it's your job to do the translation between that. Alright. SPA versus HBA. Okay. The endpoint has its own physical address space. Yes, because it doesn't know anything. The endpoint is retarded. All requests presented to the device already use. Okay. The device physical addresses. The CXL endpoint decoders have an interleave disable, one-way interleaving, and the device does not perform HPA decoding to determine a DPA. The platform provides a PRM handler for CXL DPA to system physical address space translation. The PRM handler translates the device physical address space to the system physical address for a specified CXL endpoint. In the address space of the host, SPA and HPA what? SPA and HPA are equivalent. And the OS shall use this handler to determine the HPA that correspond to a device address. For example, when configuring the HGM decoder on a platform with normalized addressing, GUID and the parameters buffer format of the handler are specified in section whatever the fuck. Oh, it's the section right under. If the OS identifies the PRM handler, the platform support normalized addressing, and the OS must perform DPA address translation as needed. Go back to work. PRM handler invocation. The OS calls PRM handler for CXL DPA to system translation using a direct invocation mechanism. Okay, but who calls PRM? Is it CXL or is it technically our CPU? The caller invocates and prepares parameter buffer, passes PRM handler GUID and pointer parameter. Fuck, I'm confused. Okay, so this is not true. That's the best way to say Rust. Bye, Rust. To achieve this, we use ACPI platform, some program creating a source language. MB based. Okay. I think I got a good grasp of this. We can do like origin. Hey. ACPI PRM was created to remove the need for... No, we're getting too deep. We're getting too deep. Okay, let's just reread and think about this a bit. AMD Zen 5 address translation enabled for use with CXL. Zen 5 system can be configured to use the normalized addresses. This feature creates a split between the addresses of the CXL endpoint, the CXL host, and the system. The benefit of this split is the ability to interleave your memory across multiple CXL endpoints, allowing for better performance. Here's how it works. So I will make a graphic that will show. So you have the whole system memory that designate a part of it to your host physical address that then splits it into smaller device physical address, which are the CXL endpoints address space. Now in this system, the CXL endpoint doesn't know about HPA or SPA. It operates off the instruction given by the CXL host, which translates and interleaves the memory addresses. All of this means that we need to translate the DPA to SPA. All of this means that when give me half a second and I'll explain this. Okay, when we will... Fuck. They have a specific reason. I think they say error. Okay, let's reverse. All this mean? All of this means that we will need to translate DPA to SPA. To achieve this, we use ACPI Platform Runtime Mechanism, PRM handlers. These small programs are created in ACPI source language. Fuck. I was right before. When encountering N, and here during profiling, tracing, or error handling, we will need to translate DPA to SPA. To achieve this, we use ACPI Platform Runtime Mechanism, PRM handlers. These small programs are created in ACPI source language. Maybe I need to yap more there. Anyway, I still don't understand how interleaving memory increases performance, since holes will cause cache miss. No. No. So, let's set this up. I hope I'll do a good job explaining it. Okay. So here we are only looking, just for clarity, we are only looking at one CXL host. And here is 4 CXL endpoints. Okay, so CXL endpoints, and it's like version 1 to 4. Okay. So the idea in interleaving, when we say that we have a CXL host and a CXL endpoint, we need to keep in mind that those are literally different devices, right? So that's like a RAM module, that's another RAM module, that's another RAM module, and that's another RAM module. So just like putting 2 RAMs inside of a system brings better performance because we can split the transaction between the two and have a better throughput, splitting the transaction between multiple modules brings us better performance. So here, when I said like every 64 bytes, you switch from one to another, this is pretty much explicitly what they're stating in the documentation. So this is not just a chunk by chunk thing. It's a stripe, just like a RAID. It's a stripe thing. So here, when you say cache miss, well, no, because from the host point of view, from the system point of view, this address space is its address space. So here, let's say that you bind this shit to address space, I don't know, like, let's create some things, 400 to 800, right? When it says go to 400 system address space, which if we were in a physical versus logical world, it would be physical address space. When you say go to 400, it is an actual place on the drive, on the RAM, right? It's just that the CXL host module will interleave all of that. So from the host's point of view, this is just a chunk of memory that you can use as normal RAM. From the CXL host point of view, it needs to throw things at different places depending on what it needs. And whenever we have an error or we want to profile these endpoints, then we need to have some knowledge of, okay, these endpoints have actually no fucking idea what they're doing because this one abstracts everything away from the endpoints. So that's why we need the translation, right? So whenever we bypass the host translation, we need to keep in mind that we need these PRM things. So just like if you were to set up a RAID 5, it would increase performance because you are using multiple disks for the same read. We increase performance by striping it across multiple chips of RAM. Does this make sense? Because I can be a retard. I think that this... Okay, I start to see. And like, I'll need to make an animation that shows the striping, right? Because if I have something that feels like RAID 5 striping. If I have something like this is not as good, but like if I have some kind of striping, I think that it becomes obvious. Especially if I like make them glow a little bit, like read on a normal system and it's like one chip, then it stops, the other chip, then it stops. But like read on this new normalized system, like everything fucking glows up. Like this would... Yeah, I'll need to read more on my own. This allows for data transfers faster than a memory module limitation because the AMD fabric allows faster speed than the one memory module. Yes, here we are assuming that the pathways, that the buses are always faster and, well, faster is not the right word, allows for better throughput than the memory chips themselves. Absolutely. Or else this is all useless. Yep. I don't know, am I explaining this well? Like, I mean, this is... Like... This needs to be explained a lot. Okay. Maybe this is fucking useless. These parameters. Oh. Oh, I know. I know. This patch. Do we create the handler? Or are the handlers provided by the hardware? I think it's provided by the hardware. So here I would say dispatch enables the management of these ERM handlers and allows for the translation to occur. And I'll probably like say, it's cool to see that CXL is making more of the Linux. Okay. All right. So this is like animation heavy. All the heavy lifting comes from this. Oh, whoops. Where the fuck did I put this? Okay, I'll put it there. Okay. And we should probably like put this. This is very fucking important. Yes, 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 yes. Okay. Good, good, good. I think I got it. Oh, damn, we've made some strive here. I'm too hungry, okay? I'm way the fuck too hungry. This is all for today, okay? I think we've done a good thing. 3 hours, goddamn. We've done good, we've done good. But like we're a quarter of the way through. And in all honesty, this is probably the hardest shit we're gonna have to do, right? Everything from here should be piece of cake. Maybe some graphic thing will be complicated. Oh, the FS is pretty heavy too. We'll go deep in the FS things. I don't know. Yeah. Good work. I was late. Not really up to date with hardware optimization. I was to go deep on FS. Yeah. Like, I know that there's been some work in BTRFS and EXT4. Didn't we check something with it last release? Next version sent out to me, improving write performance, dealing with current direct IO, or to an extent to IO completion. Oh. It may not be as interesting. Okay. EXT4 sounds like you can make big upgrades and be fucking boring. And it sounds like this is it. But BTRFS might be the thing. Like direct IO with block size larger than page size. Zone mode. Fixes. I don't know. We'll see. We'll see. Anyway. I don't know. I think we're going to make this one a bit shorter than the other. Yeah, fuck me over many times for me to be interested and use it. I don't know. I feel like it never fucked me. So I don't know. Like, it feels good. The big thing is that normally, how can I say that? The problem with BTRFS is how it was sold. It was sold as, we're going to, well, it was sold as influencer and Linux enthusiast on the internet. We're like, this is the next new thing. This is going to have all the features. This is going to be like, woohoo, fucking awesome. But then in reality, it was just like ext5. It was really just ext5. It had all the cute little things. It was way faster for traditional hard drives, like way faster. But everything else is like meh. Like, if you want something awesome, you go with XFS. The XFS team is fucking unhinged. They have no chill. When it breaks, it is too complicated to fix, while we can fix an ext4 file system. I disagree. I beat up my BTRFS pretty hard, and it survived. So no. Like, I fucked it twice. I don't know how you can do that. And, okay, did you use the RAID functions of BTRFS whenever it was broken? Maybe that's your issue. I never used the RAID function of BTRFS. When I had a RAID with BTRFS, I did my RAID outside of BTRFS because I thought that was how we should do it. Oh man, I was a Linux toddler back then. Never RAID. Oh, you don't like RAIDs? You fucking... Nyeh. I like RAIDs. Although debugging them is fucking pain. But MDAM is pretty good. For fixing. Of course, mirror is better for fixing. But, like, when I did raids, I did raid 5s. So you have one disk redundancy. I use multiple different disks for different brand. So the chance that, like, 2 were going to die on me were pretty slim. So, like, I've never had issues with that. Like, even when one of my drives died in one of my raid, like, I was able to get everything back. It is very easy, MB. It is very easy. Is it because your experience? No, it's not. No, MB, it's not. It's really not. Is your experience with hardware RAID? If you have never tried MD... I never know how to say that. Yeah. If you've never tried this, it is so fun. Okay, my RAID experience with this, I've moved RAID 0s and RAID 5s. And even one RAID 6. I don't remember why I did that one, but I've moved around RAID like this. And all you have to do is take the disk from one system, take it to the other. You tell your OS that, like, hey, there is the possibility for a RAID disk. And then what I used to do, I used to be a big Ubuntu guy. Dick, wow. disk. I went in disk, I clicked the drive, and I did this, and it worked. Each time. So, like, when you have this way the fuck too easy, like, way of doing things, I understand that it may fuck up if you're using, like, commands and you're stressed and all this. But goddamn, my GUI could do it. Anyway, it's, no, I really like how they've got it set up. Like, I think the worst pain that there is from MDAMD, MDADM, anyway, is that if ever you do a wrong command, it can, like, scan the drives for 6 hours, and you're just there waiting like a dumbass. Like, it's not breaking anything, it's just rescanning things. So that can be triggering, but no. My experience with this has been, like, such a joy. So maybe that's why I'm a raid lover, okay? Maybe your experience is the experience I need to become a raid hater. Anyway, love you, and we may see each other tomorrow. And by May, I mean if you want to be there. And tomorrow, target should be, I would like to at the very least, finish this page. And if we can get started in this, that would be great. Because we're going to run out of time if we don't. We're going to run out of time. Maybe I'll do some research offline, who knows. Because some things are boring. Alright, love you. Bye-bye.